Happy New Year, everyone, and welcome to the first seminar session of this year in the Spatial ML seminar series. And today it's my pleasure to introduce Ebby Samson, who's a second-year PhD student at Imperial College London, working with Professor George Constantinidis. And his research is all about machine learning quantization and design of machine learning data path circuits. And today he's going to talk to us about his recent work in exploring efficient FPGA implementations of the new MX numerical formats. So Ebby, thanks for being here, and the floor is all yours.
Thank you. So, good morning, everyone, and welcome to my talk about exploring FPGA designs for MX and beyond. My name's Ebby, and this was joint work between Imperial College and AMD. So first I'll go through motivation and contributions, followed by some background, and then finally our work and evaluation. So firstly, I'll tell you what MX is. MX is a number system standard that's aimed at the development of low-precision compute for machine learning. And here's a screenshot of the first version of the standard. We think that reconfigurable logic can take advantage of custom number formats by tuning the formats in hardware to the type of computation that's happening. So we wanted to see the extent to which the MX standard fits well with FPGA-based computation. So in order to do that, what we've done is we've developed the very first open source FPGA implementation of the new MX standard. And I'll give you a link at the end. You can download it and try it out and use it in your own tools. Our implementation also goes beyond what are known as the concrete types in the standard. That is, the types that must be supported by the standard. And we have a much more flexible implementation that includes all of the types that must be supported as well as others. So I'll tell you how we go beyond that and what that tells us about FPGA-based implementation of MX. And finally, within the context of machine learning implementation, you probably come across something known as quantization-aware training. Quantization-aware training is where you train a machine learning model around the quantization that happens to a finite precision number representation. So we've integrated a mechanism to do QAT for MX as well. And I'll start with a review of what quantization actually is. In quantization, we take a real-valued tensor X, and we try to compress it to some finite precision data type. And the way we do that is by dividing it by a scale factor S and offsetting it to 0, then rounding and clipping to some finite precision data type. And we also have the inverse operation on the right-hand side, where we reconstruct X with some rounding noise to make X prime. Now I'll go through an example where we quantize a vector to one of the formats in the MX standard, MX int 8. This format quantizes values to 8-bit fixed point with 2 integer bits and 6 fractional bits. The encoding for -2 is unused though, to keep the range symmetric and prevent a negative bias in the arithmetic. Let's start with this real-valued vector x. First, we calculate the scale in 0.z. In mx, the scale is set to the largest power of 2 present in the input divided by the largest power of 2 representable in the target format. And the 0 point is unused. And these choices were made in the MX standard to enable easier hardware implementation compared to using a full precision scale and a 0 point, for example. Next, we apply the scale and 0 point And notice how this brings the values into the representable range of finite precision formats, so int 8. And finally, we round to nearest even and clip. You can notice that if we multiply by the scale again, we have an approximation of the original real-valued vector with rounding noise. Also notice how the first element here has been clipped to 0, as it's too small to be represented in this finite precision format. And the scale s is used to scale different values in a tensor. And that scale can be shared across different elements in the tensor in different ways. And this gives rise to what we call block boundaries, where blocks are elements that share the same scale factor. So one obvious way to share a scale is to just have all the elements in the tensor have the exact same scaling. And that's what we have here on the left-hand side for tensor scaling. Another really common way is to use what's called a per-channel scale, where you slice the tensor up as shown in the middle, and all those slices share the same scale. And on the right-hand side, you can see what's called per-block scaling, and it's this that gets heavily utilized in MX implementations that we're going to talk about today. You can see it's much more fine-grained compared to the other scale sharing regimes. And back to the example from earlier, you can see that if we have a finer grained scale, it allows us to keep the first value rather than clipping to 0. Another thing to note is that coarse-grained scaling is typically implemented in software, while fine-grained scaling is best implemented in hardware. And this is what MX does. It uses fine-grained scaling implemented in hardware, and the block size is usually 32, so 32 elements sharing a scale. So it's on a different order of magnitude compared to per tensor scaling. These are the operations defined in the MX specification. So first, the dot operation computes the dot product between a pair of blocks that share a scale. So the scales S and T are factored out of this dot product. And next, we have a dot general operation that computes a dot product that's arbitrarily long with vectors that have multiple scales. And finally, we have conversions. So our IP cores provide conversions to and from FP32 and MX formats. QAT is a technique used to reduce the effect of quantization error on model accuracy. And this is done by training the model with quantization noise in the forward pass. And the backward pass is still done in full precision in our implementation. There are many libraries that enable QAT, but we used a popular one called Gravitas from AMD, and we extended it to add mini-float quantization and per-block scaling to support the MX standard. And now about our work. We use a library of IP cores and the QAT framework that fully supports all of the MX concrete formats, which are these MX formats here in this table. And on top of that, our work is very flexible and supports any format with these constraints on bit widths and exponent and mantissa widths. And our work also supports multiple block sizes apart from 32, which is used in the MX standard. You can also enable or disable special numbers like nants and infinities. And you can also choose between saturating arithmetic and other overflow behavior. So now I'll go over some of the blocks we have in our library. This block implements the dot function from the standard. So it factors out the scale and does error-free integer accumulation with pairwise summation, and the scale is also processed in parallel. And this is our implementation of .general from the standard. We have a converter from MX to FP32, followed by an FP32 accumulator that can be pairwise summation or recursive over time. And finally, we have cores to convert these FP32 values back to MX. So to do this, we first find the largest exponent in the block, and our library includes a comparator tree for this. But it's also possible to replace that tree and use a static value and try other implementations. QAT trains the model and adjusts weights to account for quantization error. And this is what our quantizer looks like. The red and green parts here calculate the scale, and the scale is used to quantize the input in this blue part. So the input is quantized to the target element format, and it is then dequantized back to x prime, which is a reconstruction of the real valued x with quantization error added. For evaluation, we measured the area of a quantized ResNet 18 implementation alongside the accuracy. We had a lot of formats to evaluate, so we estimated area rather than synthesizing a design for every format. And we did this by profiling the area of our IP cores by varying K and bit width. So K is the block size. And then after that, we calculated the area required to implement a fully unrolled ResNet 18 model in lookup tables. And we performed quantization by first training the model in FP32, then quantizing the trained model before inference, so just direct cast. And after that, yeah, we also quantized both weights and activations. We have two sets of results. So PTQ is quantization without any further training, and QAT is quantization followed by training with our QAT framework. The points, the QAT diagram, the QAT plot have shifted down. So the QAT did work to bring down the inference error. And the plots show inference error on the y-axis against estimated area on the x-axis. So the red and green lines are the Pareto fronts for per tensor and per channel scaling. The black dotted line is the Pareto front for MX scaling, and this gray flat line is the FP32 baseline. So first, I'd like to bring your attention to these circled areas. These are concrete formats in the MX standard, and all of the other points outside of these red areas are custom formats. So you can see that a lot of these custom formats also lie on the Pareto front. If your workload requires baseline performance with no loss in accuracy, you can see that MXint8 is a good choice before doing QAT. But after QAT, MXint7 also keeps this baseline accuracy with lower resource usage. And if a minor degradation in accuracy is acceptable, the MX FP6 formats are good options before QAT. And after QAT, int6 and int7 formats with large block sizes give a better trade-off. And finally, if low area is the priority, custom MX Int5 formats dominate both PTQ and QAT scenarios. And you can also see the effect of the QAT framework through MX Int4, which is circled on both sides. After QAT, MX Int4 is a much more viable option. Its test error was usually above 40% before QAT. And here are two QR codes. On the left-hand side, you can download our IP course and you can take our RTL and try it out in your own projects. And on the right-hand side, you can download the QAT framework. It works with both PyTorch and Gravitas. And yeah, please do use them and tell us what you've been able to do with them. And thank you very much for your time.